Hello student, today we are going to learn de-Broglie's hypothesis and derivation of de-Broglie's equation. The de-Broglie's hypothesis. As Einstein suggested that light has dual character as a wave and a particle. That means the photon is having a particle character as well as the wave character. Similarly, de-Broglie proposed that matter also has dual character as a wave and a particle. Thus, electron have a particle character as well as wave character. He derived an equation to calculate the wavelength of electron of mass m and velocity v as lambda is equal to h upon m into v, where h is the Planck constant and lambda is wavelength of which is associated with that particle. The equation is known as de-Broglie's equation and the wavelength calculated by this equation is known as de-Broglie's wavelength. Now, the derivation of de-Broglie's equation. According to the Planck's quantum theory, energy of a photon is given by means of equation E is equal to h nu, where E is the energy of photon, h is the Planck constant and nu is the frequency of the radiation. Now, this is the equation number 1. The energy associated with the photon of mass is given as, according to the Einstein, if the photon is having a mass m, the Einstein's equation is given as E is equal to m into c square, where c is the velocity of radiation. Now, this is the equation number 2. Now, the equation 1 is according to the Planck quantum theory, equation 2 is according to the Einstein's equation. Both are giving the energy of the photon and therefore, this left hand side of both equation is the same. Therefore, we can say that from equation 1 and 2 that right hand side should be equal or the same, and hence we can write h nu is equal to m into c square, equation number 3. But nu is equal to c upon lambda. What is c? C is the velocity of light. Lambda is a wavelength of the radiation. Put this value in the equation number 3. Here we can put the value of nu c upon lambda. Equation 3 becomes hc upon lambda is equal to m into c square. Now, c get cancelled, we will get h upon lambda is equal to m into c. If we rearrange this equation, we will get lambda is equal to h upon m into c, equation number 4. Now, this is the equation. Here we get lambda, that is a wavelength, is equal to h Planck constant, m is the mass of that photon and c is the velocity of radiation. But mass into velocity is a momentum, it is represented by letter p. The equation 4 can be written as lambda is equal to h upon p. H is the constant, therefore we can write lambda is inversely proportional to the p, or p is inversely proportional to the lambda. Lambda is a wavelength, equation number 5. Now, this equation 4 or 5 is for the photon of a radiation, but this equation can also be applicable to the any material having a mass m moving with velocity, and therefore that wavelength associated with that material or that mass is given by means of lambda is equal to h upon m into p, equation number 6. Now, this equation 4, equation 5 and equation 6, these three equations are known as de-Broglie's equation, and the wavelength given by the equation 4, equation 5 and equation 6 is called as a de-Broglie's wavelength. In this way we derived the de-Broglie's equation. Now this de-Broglie's equation can be applied for the any material of any mass. Now this can be studied with the help of the two examples. Let a body with a large mass. Let us consider a stone of 1 kg moving with velocity 2000 meter per second. The de-Broglie's wavelength will be given as lambda is equal to h upon m into v. H is the Planck constant, m is the mass, 1 kg, v is the velocity 2000 meter per second. If you put the values, h is 6.626 into 10 to the power minus 34 joule second, mass is 1 kg and velocity is 2000 meter per second. Put in this formula, we will get these values. If you calculate it, it is 3.313 into 10 to the power minus 37 meter. If you convert it into angstrom, it will be 3.313 into 10 to the power minus 27 angstrom. If you see the magnitude of this wavelength, it is in the range of minus 37 and the mass is 1 kg. To compare with this mass, this wavelength associated with this stone is very small, and therefore it cannot be measured by means of any instrument. When mass is large, wavelength is very small. Now similarly, we can find out a wavelength for a body with a small mass. Let us consider electron. It is having a mass 9.109 into 10 to the power minus 31 kg, and that of the velocity, it is 1.20 into 10 to the power 5 meter per second in an orbit. The de-Broglie's wavelength will be given as, again, lambda is equal to h upon m into v. H is the again same value 6.626 into 10 to the power minus 34 joule second. Mass of the electron is 9.109 into 10 to the power minus 31 and velocity is 1.20 into 10 to the power 5 meter per second. If you calculate it, its value is 0.6061 into 10 to the power minus 8 meter or 60.61 angstrom. If you compare this wavelength with that of the mass is in the range of 10 to the power minus 31 and wavelength is in the range of 10 to the power minus 8. It is too much large as compared to its mass, and this value in this range can be calculated by means of an instrument. Thus we can calculate a wavelength for a large mass and also wavelength for a small mass, but the wavelength of large mass is very small and the wavelength of small mass is very large, and it can be measured. In this way we can calculate the wavelength of any material or any matter which is having a dual nature, that is, or dual character, that is particle character as well as wave character. Thus we can measure here the de-Broglie's wavelength for any particle. So this is about de-Broglie's equation and its derivation. Thank you.